All right, greetings. I'd like to welcome everybody to the October 2025 DAS monthly meeting. So first item on the agenda, do we have any new members who would like to introduce yourselves? Anybody here? Can I turn this around for you? Tell us.
Bill Knoll, I just moving into Delaware. I've been a member of the Astronomical Club up in New York for 40 plus years.
Awesome.
Welcome.
Awesome. Anybody else who hasn't been to a monthly meeting?
New members or guests?
Anybody?
Oh, yeah, go for it.
Say hello.
My name is Jeff. Just moved to Delaware about a year ago. Was involved with the Delaware Valley restaurant for a good bit of years. So looking to probably join here.
Awesome.
Very cool. You can always join more than one club.
We're not exclusionary.
Any other new members?
We allow dual citizenship.
All right, very good.
Yeah.
So next item on the agenda is DAS dues. You want to talk a little about that?
All right, it's November, so we're starting the annual dues collection process. Dues remain $30 per year. So basically gets you for all 2026. And you should have gotten an email from me 2 days ago if you haven't paid your dues yet. And there's like 4 different ways you can pay, a couple PayPal options, one which doesn't require a PayPal account. So you click on it, you push your credit card information and you don't have that PayPal. You can pay at any club meeting or the workshops on Tuesdays, to any board member that you can give the money to them if I'm not there. Or you can mail it to me, and that's in the newsletter and also in the focus and the website and all sorts of places where you can get to see where to mail it. So we're starting the dues process. We've had 40 people already sign up for 2026, so that's great. It's about a quarter of the club, and of course the dues go a long way to help make the program what it is. So we encourage everyone to renew for next year. Thank you.
Wonderful, thank you. You're good. I want to turn it to Lynn King. I want to talk about county.
Okay, I'm not going to say that. For those who ordered calendars, I do have them with me. And also, if there's anybody here that has not ordered an observer handbook, come see me after the meeting and I'll get the name. And I will be putting in an order. I'm looking for 5 more, and then we get free shipping plus a hey, shipping can be expensive on some of these things, as it is now. So if I get a minimum order of 10, then we're discounted for $26 a book plus free shipping. So see me after the meeting. And then if you, like I said, if you ordered a calendar, I do have them here with me tonight.
Very cool. Very nice.
Thanks as always for coordinating that, Lynn. That's awesome.
Yeah, you do a great job. All right, so next we have the APC. So you want to talk about that?
Okay, yes, the next meeting of the APC is going to be on Saturday, November 15th. That's astrophotography special interest group for new members. So the special topic presentation will be Computers for Imaging Part 2, and we'll be focusing on mini and micro PCs as well as Windows machine, including Windows machines and the ASI Air. And announcements, as always, will go out over das.groups.io ahead of the meeting. So pay attention to the groups.io for announcements.
All right, thank you. Next item is the book club. Mary, do you have anything?
Yes, I have the announcement for the October book club meeting. We'll be meeting on Thursday, October 30th at 7 p.m. Eastern Time via Zoom. And we will be discussing a book by Marcia Bartusiak, Black Hole, How an Idea Abandoned by Newtonians, Hated by Einstein, and Gambled on by Hawking became loved. Marcia will be joining us for our meeting. We'll also have a special guest I will not name who will be joining us, but I think everyone will be very pleased to see her. And David Ives Brown, who is a retired JPL engineer in California and a retired Rittenhouse Astronomical Society board member, will be leading our meeting. And I do want to just also hawk our November meeting. If you have not read Starlight Nights by Leslie Peltier, we will be discussing that book. It was published in 1965 by one of the most famous amateur astronomers. And the 1999 edition was, a foreword was written for the 1999 edition by David Levy. And David Levy will be joining us. And he's one of probably many people would say the most famous of amateur astronomers. And Andy Edelin, a new member of the DAS and the author of a article in the Sky and Telescope magazine about galaxies in the summer triangle, will be leading the meeting for us. Your guests are invited to join.
Very nice. Thank you very much.
And please send the link to the meeting and information about the meeting to anyone in your circle, because we do consider these meetings to be public outreach. So if you're not a member, you're most welcome. Just email librarian@delastro.org. We'll put you on the list.
Cool.
Thank you.
All right, next, Jim, do you have anything for outreach?
Oh, yeah. We've got, we had a really good outreach event at Lum's Pond State Park Campground on October 4th, where we basically we participated in the Becoming an Outdoors Woman program. And basically what we did is we showed these outdoors women how to find the North Star and various asterisms and constellations and whatnot. And then we, Sydney and I basically showed them views of Saturn and various constellations. They were amazed at what Saturn looks like now. But got raves about how it looks like a dot with a line through it. Dot with a line through it.
Yeah.
So what we've got coming up is on Monday, October 27th, this coming Monday. We've got a DAS outreach for the Sapling Society of Delaware. That's a homeschooling outfit sanctioned by the state of Delaware, and they focus mostly on nature education, and very heavy emphasis on STEM education. Then on November 1st, we have a star party with the DAS at the Delaware Museum of Nature and Science on Kennett Pike. And the Saturn and the moon will be 2 degrees apart in the night sky, and we'll still see the summer triangle and other constellations. Let's see, and on the 21st of November, that's a Friday, from 7:30 to 10, we'll see, we'll have Cocoa and Constellations at the Newark Reservoir on Old Paper Mill Road. And this very popular event is sponsored by the Newark Department of Parks and Recreation. So that'll be wrapping up the month of November doing that.
Oh, very nice.
And I highly encourage folks, new people, advanced people, but the emphasis on new members. Outreach is a great way to get more involved. If you think you don't know enough to do outreach, you're wrong.
Exactly.
If you think, well, I don't have a telescope, you're wrong, because you're part of a club that has about a dozen of them that we can loan out to you. So come on maybe a Tuesday workshop prior to the outreach event, or tonight you could go home with one. Outreach is a blast. I mean, as Jim alluded to, I can never get enough of sharing someone's first view of Saturn through a telescope. I've done it hundreds of times and it's still awesome. And plus it is our mission.
Yeah,
Absolutely.
So, thanks, and Jim, awesome job coordinating all those events.
Thank you.
It's really cool.
All right, one more thing I want to point out to people is there's a fantastic comet in the sky, Comet Lemon. It's in a great spot. I viewed it for a couple nights in the last couple of days, on Saturday and then on Monday. I looked at it both days. I took photos of it. It's a beautiful thing. So definitely go out and check it out. It's got a beautiful tail, a nice ion tail in the middle of it. I saw it in binoculars and I saw it in my camera. So definitely go out and check that out. About 7 to 8 o'clock. It's in a good spot to view. All right. And without further ado, we can start
Right on.
the meeting.
All right. So actually, for the next 2 months, we have actually a very special 2-part program. I don't think I've done that a whole bunch in the past, but I saw a really awesome opportunity for that. To sneak up on it, I think it's a pretty inarguable statement that the telescope, the single biggest invention to advance both professional and amateur astronomy alike. I'd make an argument that the second most significant invention to advance astronomy has been rocketry. Without rockets, you don't have Mercury, Gemini, Apollo, Hubble, Webb, New Horizons, any of it. And I would challenge anyone to tell me what invention furthered astronomy more than rockets other than telescopes. What's maybe not so commonly known is the role that this region has played in the development and advancement of rockets. And there's a company that's gone by many different names, currently Northrop Grumman, located in Elkton, Maryland, that I'm very proud to call my employer. We develop, build, and test solid rocket motors in Elkton, Maryland. I've been there for about 2.5 years, so I'm still learning a lot. But for the next 2 months, our 2 speakers are coworkers of mine that each have on the order of 45 years of experience each. And so over the next 2 months, we're going to be have the privilege of experiencing a lot of wisdom and knowledge in this area. Tonight, we're being joined by Dave McGrath, who is going to give a tremendous history of rockets and specifically rocketry in the local area. And then next month in November, we take a little darker turn. Sherry is going to be talking about the Challenger disaster. The company is currently called Northrop Grumman. It used to be called Thiokol. Yes, we made the famous O-ring. But Sherry was actually starting her career right in the midst of that and has some unique experiences and perspectives and wonderful insight. And so next month, she's going to be sharing a really cool story about, obviously a tragic event, but that'll be very interesting. So sneak peek towards next month. Tonight, welcome Dave to talk about rockets in the local area. And Dave, all yours. Do you need the do you have your file? Is it up or?
Yeah.
Okay, I'll just let you. You got it from here.
Yep.
Okay, cool. Dave McGrath, everybody. I think are folks online seeing Propelling History and the photo of the moon landing?
One of them. Quick quiz, which one is it?
Are folks online seeing the presentation?
Not yet, no.
Okay, Rob, can you help? I'll embarrass myself. Thank you for your patience, Dave.
Yep, no problem.
That Dave Scott or Tim Irwin on?
Uh,
I think it was 15. It was Apollo 15. 15 in the hills. Badly wrong.
I thought I'd already done that, but
That's okay.
And yeah, get Rob, get
Dave.
Dave on the, yeah, there we go.
I'll pin him.
There we go.
There we go.
Right
Yep.
on.
All right, take 2.
I can't get the thing because it's hidden at the bottom.
Oh, with that pesky little. There you go.
There it is. Is this one?
I think it's in the browser. Yep, there you go.
All good now?
I think you got it from here, Dave.
Yep.
Okay, awesome.
Should be good.
All right.
okay,
Yeah, I think you could do that. That works.
thanks for having me. It's a pleasure to be here tonight.
talk about the place I worked at for
Oh,
a little over
let's-
40 years. You guys guessed it, this was Apollo 15, and Elkton supported all the Apollo missions, and I'll get into that as we go through the presentation. But I worked there for a little over 40 years, ended up being a senior fellow from Northrop and also an AIAA fellow, American Institute of Aeronautics and Astronautics. So going to give you a little history of Thiokol. Thiokol Chemical was the first name. There's been 7 more. It was Morton Thiokol when I started. Then it was Thiokol Propulsion after the Challenger accident, and Morton went their separate ways. Then an investment set of banks bought us, and we were courting Thiokol Propulsion. They sold us to Alcoa Thiokol Propulsion. Then they sold us to ATK. Then Orbital Sciences and ATK got together to be Orbital ATK. And then Northrop bought us in, what was it, Sherry, 2019, 2018, somewhere in that time frame. So I'll do a little bit of the early history. I've got several bullet things. I'm not going to read them all about the Elkton site. And then just some selected efforts across the decades. There's so many of them. It's hard to pick which ones are the most appropriate for a kind of a short presentation. I could go on for hours because I did several papers in the AIAA on this. So almost 100 years ago, Joseph Patrick discovered a process for the first synthetic rubber as a polysulfide binder type system. He called it Thiokol, which was Greek for sulfur and glue. The 2 Greek words put together was Thiokol. So there was a patent issued. They formed a license company. It was used as a sealant, lots of different gasket type materials over the years. They moved to New Jersey in 1930. And then they continued to work on it and through the World War II years. And it was used everywhere in bombers, airplanes, fuel tanks, gun turrets, etc. After the war, though, they started selling a lot of the polymer to this place called Galset, which is really GPL now. It's Guggenheim Aeronautical Labs at Caltech. So marketing guys went out there to find out what was going on. They said, "Hey, we're making solid rockets out of your polymer, using it as the binder system. You guys ought to get into this business." So they take a couple more years and finally get a contract to work on it. And they looked for a site all around the New Jersey and local area here and found an old armament site in Elkton, Maryland, which then became the first site for solid rockets within Thiokol Corporation. And that was in 49. So we were about 10% of the company's sales at 150K back in that time frame. Got some people from DuPont. Obviously, the explosives and gun propellant business is very similar to what we do in solid rocketry. Brought some of those employees across. And then in 48, they hired their general manager, Lou Willinetz, and the first motor was fired, built in a building that's no longer there. There's now a new facility on that corner in the rocket site doing advanced composites work. But that was the first motors, a little test motor that was fired. The Army was a big customer at the time, and they said, move everybody to Huntsville, to the Redstone Arsenal, because they were doing a lot of work on missiles then. And quickly they scaled up, from these little rocket motors, a few inches in diameter, all the way up to 31 inches in diameter on the Hermes that was fired in 1951. And then the Air Force wanted to do some solid rocket work, and they were darn sure they were not going to put a contract into an Army base. So Thiokol reopened the Elkton site in 51 in the summertime in July, and worked on jet-assisted takeoff with ammonium nitrate oxidizer. So basically fertilizer as the oxidizer. 53, still only about 20 people. It's pretty small group of folks working there. Early in 54, there was not a lot of work there at the Elkton site, and Huntsville had an abundance of work, so they transferred several programs up there to Elkton from Huntsville, Alabama, and continued to do some work. 55 ICBMs were starting to be worked on, and again, another group of folks came up to Elkton. During that time, the first air-to-air missile that the U.S. produced, the Falcon missile, was produced at 3 sites in Thiokol, actually. Huntsville Division, the Elkton Division. Elkton made over 10,000 Falcons in the stretch of time that was the missile of choice before Sidewinder. You've maybe heard of Sidewinder recently, or AMRAAM. And then the Longhorn Division in Texas. The site in Texas is now where SpaceX does a lot of their work. So some of these sites continue to be used over time. One of the first efforts going into space was for the X-17. It was a multi-stage solid system. We had the upper stage, the recruit motor, about 9 inches in diameter, about 9 feet long. And what the purpose of the X-17 was to propel up to a high altitude, then get across the apogee, and then accelerate down into the atmosphere to test materials for reentry vehicles, for ICBMs, and for ablative heat shields for the capsules that they were intending to make. So fired off a ship, the USS Norton Sound, that also saw some liquid rockets fired off of the Norton Sound. So that you think of some of the later systems that launched off of ships, that was first done in the 50s with liquids and solids. So over 40 flights were conducted on that program. The Recruit saw life for a very long time, over 40 years of production. One of the first things that went to really high altitude was Project Farside. So there was 4 Recruit motors as the first stage and a single Recruit motor as the second stage, and then various camera and other sensor systems as the payload. But it was the 0 stage, if you want to call it that, was the balloon that was carried up by. So they went to very high altitude and then ignited the rockets and flew right through the balloon up to a very high altitude to get some good data in space. It was also used on the Little Joe for testing the abort systems for the Mercury capsule. Little Joe was also used for the Mercury system and the Apollo system for the abort activities. So interesting things done with that. Elkton, at about the same time in the mid to late 50s, got into a lot of sounding rocket work. So Cajun was one of the motors that was used. The Nike interceptor system was the first stage. So Nike Cajun was the combination there, and did a lot of upper altitude investigations and various things. There was a bunch of other motors we called the Indians, the Apache, the Iroquois, Tomahawk, Cherokee, and the Sandhawk and Yardbird. They were all very high LRD type motors, very easy to make, very simple programs, but they provided a lot of upper atmosphere data for what would be used in the X-15 program and various other high-speed systems. So about 1960, remember 53 or so, there was about 20 people. By about 1960, it was a little more than 600 at the Elkton site. And those were all the things they were producing. So the Discoverer and Mercury capsule, which I'll talk a little bit more about, are these 2 guys here. Titan Vernier. So this motor was actually thrust vector controlled up for the Titan missile by holding the sides of the motor and basically moving the entire motor. And when they got to the right speed to release the warhead, they would blow the nozzle off to terminate thrust. So that was kind of a neat motor. The Titan retro, stage 2 retro for the Titan missile is this one over here. I worked on that in the late 80s after Challenger went down. Titan IV was the system that was hurried into development and used as the Challenger accident investigation was going on. So they needed to continue to launch payloads, and the Titan IV was brought in. We had to do something different with the motor, though. We had to make it cleaner burning because if you remember the Titan IV, the payload fairing overhung the basic diameter of the missile. So because we were pointed up to retro the second stage to keep it away from the payload, it had to be a cleaner exhaust to not impact the payload systems up above. The spherical rockets, the 40-incher and a 20-incher, those were done for NASA Langley to investigate upper stages, which then became later our Star Motor line. This guy right here was a seat back rocket. We were also into seat back rocket eject systems. That one was for the B-58 Hustler, which was a Mach 2 supersonic bomber, intercontinental bomber that the US had for a few years, about 10 years or so, but we made the ejection seat. A lot of the sounding rocket motors are there up behind the inspector there doing the staging for the picture. This engineer, Bob McCafferty, I worked with when I started. So I wanted to honor him. He taught me a lot of good things. Work with him on a motor that was similar in shape to this for a different application, but he was part of the Discoverer capsule return for the film packages for the Corona spy satellites. The cover story was, we called our motors the STARV for Small Animal Return Vehicle. That was a cover story. The Discoverer name was also a cover story for the Corona satellites as well. So that motor turned into the Mercury retro for the Mercury capsule to bring the astronauts home. And this is a picture of one of the cargo planes from the Air Force picking a film package out of the sky. So they weren't all successful. In fact, it took till Discoverer 13 to get the first successful return. So you can imagine the trials and tribulations of trying to snag something out of the sky.
13 is not always bad luck.
Not always bad luck, exactly right. So again, those motors, slightly different version, 13-inch diameter from about 10 inches on Mercury. 3 motors were used on each Mercury flight. 4 were used on the Gemini flights. And we were a part of all of those early space flights. If our motors didn't work, they didn't come back from orbit. The Star 13, that was part of the Mercury retro system, became the propulsion system for the first GEO satellites. So I remember actually as a really little kid watching the Tokyo Olympics, and it was broadcast by satellite from the Syncom satellite. So that was kind of a cool thing. Just a few of those were launched, and as time went on, the satellites got bigger and bigger, and the propulsion got bigger and bigger. On the military side, in the early 60s, we were part of a program called Subrock. So this system was used, come out of the torpedo tube, use the rocket to swim underwater, broach the surface, go down range, and have a nuclear depth bomb to attack the Russian or Soviet submarines downrange. So it was operational in 63. I remember seeing tests of those after the INF treaty was signed in the 80s. We had to destroy all those rocket motors as part of the treaty, and they basically static fired them at our facility without getting any data, but it was pretty impressive to see those tests. We were also part of a program called Dinosaur. It was a manned space plane program that was ahead of the shuttle. We had a program for about a little over 2 years. In that time, they tested about 18 full-scale motors from a clean sheet of paper, developed a TVC system, developed a special human-rated safe and arm and initiator system. It was intended for, depending on the flight profile, either to accelerate it to be a skip glider to go long distance, to do crew escape if the launch vehicle, which would be a Titan rocket, if that had an issue, or deorbit it if they went actually into orbit and had to come back down. So had multiple uses. Program was canceled in the not too long after the 63 timeframe by Robert McNamara, the defense secretary at the time, and program never happened, which was a shame. They developed a lot of cool technology. Some of the same four nozzle technology was used on the Minuteman first stage, Minuteman missile first stage, and Elkton did not only a little bit of the TVC work initially for Minuteman, also did some of the early propellant development work that got transferred out to Utah when the Utah facility was opened in 1958. One of the first big historical things we did was landing on the moon with Surveyor. We provided the majority of the retro burn from the orbit that they were coming in on from Earth, and then vernier liquid engines that were developed by Thiokol's liquid division up in New Jersey, Reaction Motors, did the vernier propulsion for the Surveyor. What was interesting about Surveyor was how lightweight that phenolic nozzle was. It was actually lighter than our later carbon-carbon nozzles, but it couldn't burn as long as a carbon-carbon nozzle. It was very, very simple overall, but very hard to make. There's like 24 steps of laying up material and putting it in an autoclave, putting it in a hydroclave, getting another layer on and curing that as it went. But it was embedded into the motor. You can see almost halfway up in the spherical motor is how far the nozzle extended. So pretty high embedment, and most of it was phenolic on both sides with a fiberglass backbone to keep it strong. But again, it didn't have a long burn time. Those motors are about 35-second burn time compared to some of the later ones. But several successful missions to the moon. One that failed late in the motor burn was never determined if it was a problem with our motor or whether it was a problem with the spacecraft itself. That mission failed. But I suspect it might have been a nozzle problem, because on the DMSP program, a similar design to this that we made later on in the late 90s failed at about the same time. And it was determined that it was a problem in one of the 24 steps to build the nozzle. But interesting program, and it really showed that, yeah, the surface was strong enough that you could actually send astronauts to the moon. So that was an important program. Apollo, I mentioned we were on the each Apollo flight, 13 motors each, 8 first stage retros, 4 second stage retros, and the tower jettison motor up at the very tip of the spear there. Overall, the company had another 2 ullage motors on the 3rd stage from the Huntsville division. And they also had a ullage settling motor on the 2nd stage from what was Rocketdyne at the time at McGregor, which then became Hercules, which then became ATK as time went on. So had quite a few propulsion systems, and not much is said about the solids on the Saturn V, but there were an abort motor, a pitch motor in the tower, and the jettison motor. Again, the 3rd stage, 2nd stage, and 1st stage retros, and then even the mortars for the parachutes and whatnot on the capsule itself. I had seen each of the 3 Apollo vehicles that were left. One's in Huntsville, one's down at the Cape, and one's in Houston. And I could never figure out where our 1st stage retros were until I found this report that had a picture of how they were actually installed. The problem is, on the outer cowlings, there's no door for the plume to come out. So these motors burned in about 1 second each, about 90,000 pounds of thrust each. And they actually burned their way through the cowling in that time. So that was why I could never figure out where the installation was from seeing the hardware. Obviously, they didn't have the live propulsion in there because that would be too dangerous for a museum type display. But wasn't until I found that picture that I figured out where the heck they were. As was discussed by Jeff, a lot of things happened with the Pioneer 10 and 11, Voyager 1 and 2. They were propelled by our Star 37 motor to get on the grand tour that went through the outer planets. Lots of amazing discoveries by those spacecraft, which are basically still operating at a low level, some 50 years later. But we set the speed record. So we continued on many of these missions to set higher and higher speed records with these spacecraft with the launch vehicles. But only man-made objects to leave the solar system were propelled by our motors. The first commercial spacecraft launches from shuttle were propelled by our motors. Hughes, now Boeing in LA, 376 spacecraft. We had a Star 48 as the perigee kick, and up in the assembly itself was a Star 30, 30-inch diameter motor, 48 being a 48-inch diameter motor. So about 4,400 pounds of propellant in the big one, about 1,000 pounds of propellant in the upper stage. First ones ever launched out of the shuttle were propelled by us. First ones retrieved were put in an orbit. So there was 2 failures, West Star and Palapa satellites. The Star 48 nozzles failed in flight, and the Star 30s, they were kind of waiting around in a non-ideal orbit to be retrieved. The Star 30s were then fired to put them in an orbit that the shuttle could later retrieve them. So both those motors came back. I looked at them, part of the team looking at those when they came back, and they burned much like our static tests at the Arnold Engineering Development Center in Tullahoma, Tennessee. So that was kind of an interesting revelation that, you know, the spin that we put on it there didn't have the axial acceleration, but the spin acceleration was dominant over the axial in that case. But so that was kind of interesting to see. Trips to Mercury, Venus, Mars were also done. This one being Magellan mission. So the lower stage is the IUS, built by Chemical Systems Division of United Technologies at the time. They're no longer operating. Our Star 48 was under the spacecraft there for Magellan, and it was fired. That's the longest in space of a solid rocket before it was fired, 462 days. And before, as they were doing the final integration down at the Cape, one of our technicians from our plant was part of that team, hooking up all the lines for the safe and arm and whatnot to the various spacecraft systems. And he noticed that the drawing was wrong, that the safe and arm was going to be wired up backwards. And he called back to the plant. They double checked it. They agreed that the drawing was wrong. He hooked it up right, and it went successfully. Had they not done that and just followed the drawing, nobody would have really known why it didn't fire.
It would have gone backwards, right?
No, well, it would have come around Venus, and they would have picked it back up, but they wouldn't have understood why the motor didn't fire.
Yeah.
So yeah, it was an interesting thing. He got a NASA award for taking care of that problem. Part of the video that I have has some of the controllable solid propulsion stuff that we've done over the last 40 years. The first hover tests by a controllable solid were done on the LEAP program, lightweight exoatmospheric projectile. So I'm sorry if I use acronyms. I'll try to spell them out as I go, but that was a technology program that we started in the mid 80s and it went to the early 90s. The hover tests were in 93 and 94. The Hughes system became later, they were bought by Raytheon and became part of the Standard Missile program. And the program we had after that was a scale up really of that propulsion system. Going to Mars, we developed the retros and the airbag inflators for the Pathfinder and the two MER, the Spirit and Opportunity missions. I was the lead engineer for the retros for Pathfinder and helped with the IR&D tests, the internal R&D tests for the airbag inflators. Each of those lobes is 6 feet in diameter to give you an idea how big they are. So we had multiple gas generators that filled up the airbags. We worked with ILC in Dover that they did the bag material and they did the system integration of that and worked directly with JPL on bringing that to fruition. But that was the first soft landing with a solid on another planet. The SM-3 program, I mentioned that, Standard Missile 3. It's been used a lot recently, defending Israel against a lot of those rocket attacks from Iran and the various others. We made the divert system, solid divert and attitude control system, or SDACs. We made that for the Block 1 and Block 1A versions. We're now on Block 1B. Aerojet makes this front end system. But I have a video on that that'll show you what that system can do, but pretty amazing. We also have data on being in orbit for a lot longer because of the Challenger accident. The long duration exposure facility was in orbit for a lot longer than it intended. We had, as Thiokol, a lot of different materials on board, propellant samples, bond line samples, nozzle samples, insulation to look for outgassing and changes in the propellant characteristics, mass, did it outgas, did it not outgas, those sorts of things. Those came back and really showed that we could actually have missions to the outer planets. We had a technology program here a couple of years ago for a Europa lander. The lander portion hasn't been funded, so the motor development really didn't hit high gear, but we got a lot of the technology data in place to support a mission out to those kinds of timeframes. They were talking about close to 9 years of flight time before they would use the motor, and we felt confident based on the LDEF data that we could do that.
When was this?
The program was probably 4 or 5 years ago now, as part of the technology effort. The orbiter for Europa, I think, is about to be launched or was just launched this year. And it's about the size of a bus. So it's a pretty big system. The lander was going to go on a different mission if it got funded. Basically, the orbiter was going to scout areas to try to land, and the lander would come in later and come in and land near a fissure, an open fissure in the surface to see if they could find life. We've since looked at that using that same data to go to the Saturn icy moons. They also think those with the liquid water oceans under the ice might hold life. So that mission may yet happen, but we haven't seen any technology funding to look at that yet. So this is a quick overview of the propulsion system. I showed you that Titan Retro picture early on from the early 60s. The motor for the Pathfinder Retro, that's a Titan Retro. It's just 3 times longer and a canted nozzle instead of a straight nozzle, but basically the same type of case inner dimensions and end cap type designs were used on that one. The airbag inflator was kind of interesting because we had 3,000 degree low flame temperature gas, 3,000 would seem very hot, but most of our booster propellants are about 6,000 degree flame temperature. About 3,000 degree gas goes through a solid coolant that sucks up the heat and generates gas. Comes out about 600 degrees out the end of there to inflate the airbags. And so that was kind of a neat technology development. The thickness of the coolant chamber was about 15 thousandths of titanium. So one of the times one of the machinists was trying to clean something up, he ran a screwdriver right through the wall because it was not very thick. 15 thousandths, not very thick. Same basic design for the MER missions for Spirit and Opportunity. So from really a microwave oven size rover to a garden tractor size rover is the difference between that first mission and then the other two. The Perseverance and Curiosity rovers, those are about the size of an SUV type size rover, so much bigger. Retros were scaled up. We had a tangential rocket, that's the Tears rocket, just in case the winds on Mars were too high. They wanted to be able to drop the bags down pretty much vertical, basically arrest the motion against the wind if there was wind on a landing day. So that was a different motor development that we got to do in the early 2000s. So New Horizons, that was the first mission to Pluto. We supplied a Star 48. It was launched in 2006. The motor fired not long after that, but the encounter didn't happen until 9 years later. Kind of says how far out Pluto is. And the spacecraft is still exploring in the Kuiper Belt. So that's it's a cool mission. Found out a lot of things about Pluto along the way, and again, set another record for the fastest object at the time. So the attitude control motor, I was the lead engineer on that. Sherry brought me back from Utah. I've been the lead engineer on a flight test of the Ares 1 rocket, which got canceled by President Obama in early 2010. But Sherry brought me back in 2007 to head up this program. And it's basically a controllable, throttleable, solid rocket motor. We did a lot of development. It was pretty complex, fault tolerant on the control side. So we had 2 computers and a voting computer as part of the control system. Each of the actuators had 2 motors, one driven by one computer, the other driven by the other. So one was kind of dormant unless the primary one had an issue, but both were doing the same calculations, and the voting computer was keeping track of the health of both sides of the system. It had 8 nozzles around a 32-inch diameter. So the valves, they're about the size of a coffee can. Okay, and then the actuator makes it about a little over a foot long in total. Very high thrust, over 7,000 pounds of thrust capability in all the different directions. And I have a video of that too, from overhead, and then one of the altitude abort flight tests. So the pad abort happened in 2010. Then we had a hiatus because the abort system was way ahead of the capsule and the capsule systems. So they spent a lot of time between 2010 and about 2017, 2018, working on the rest of the Orion capsule systems. And we had kind of just low-level maintenance funding to get the design of record up to the full human-rated capability needed. Parker Solar Probe, we were part of that as well. It flew on a Delta IV Heavy, and you can barely see the motor underneath the spacecraft against the huge size of the core stage of the Delta rocket, Delta IV rocket. It set another speed record, and it's still setting speed records as it continues to do those close passes of the sun. It's getting a lot of great data, and it's been cool to be a part of that program as well. Mars Ascent. This one is painful in the sense that our contract to develop the first and second stage of the rocket that'll bring back the samples Perseverance is collecting was canceled. The whole program's in doubt at the moment. They're trying to resurrect it, but they have a cost problem. And so that's been a challenge to keep the cost down. NASA likes to give us a lot of help. They gave us a sole source contract, but wouldn't let us alone to do our work. But first and second stage motors have been fired at this point. They were ready for the qual program, and then all the funding issues have happened. I started working on Mars Ascent in about 1994. We won our first study contract. So for nearly 30 years, we were doing different studies. We were a supplier, we were a prime, and one of them we beat Boeing and Lockheed as a prime to integrate the whole return rocket. Then we were a sub again. It went through a lot of different iterations. Motors as small as 13 inches in diameter. The current one is about 21 inches in diameter on the first stage, 15 inches in diameter on the second stage. As big as 27 inches in diameter. NASA Marshall was looking at one point. That would have been really hard to land. That's a lot of mass to land, basically thumping against the ground horizontally. That would have been tough to design to. But right now that's in hiatus. We're ready to go once the program gets the go ahead. It's hard to tell what's going to happen. Whether Elon's Starship demo flights to Mars will carry something on it to try to get those samples back is one possibility, but really they got to get the cost in, and that's been the challenge over the last several months, last almost a year, I guess now.
Dave, quick interjection with, very, very recent discoveries of the samples that could potentially have life. Any sense that may have reinvigorated this?
It's unclear because the administration is reorganizing a lot of stuff in the space program. This was under space science, and they basically gutted that part of the budget for NASA.
Mm-hmm.
They could potentially bring it back to life depending on what happens with SLS and Orion. Those are the two, and Station. They're going to deorbit Station in 2030. At least that's the current plan. That'll free up money if some of those other things are canceled. It's hard to tell. It's hard to read the tea leaves right now. I mean, it's almost at the mercy of the whim of the administration, which, we had just done, a pad aboard flight test. And I guess Obama had canceled the other part of the Constellation program, which had been ongoing in early 2010. So a lot of programs we worked on have been canceled. The Kinetic Energy Interceptor was canceled with a vehicle on the pad ready to fly. Sherry was part of that program. So depending on what various administrations decide, some of our programs are at the mercy of those decisions. So it comes and goes. This one is going to happen. It's just a matter of how it happens. I mean, there was a earlier artist conception. This is off of actually a CAD model and a movie. So if you want to look at Mars Ascent on the NASA site, there's actually a really cool movie that they do of what this flight would look like. There was an artist's conception of, a vertical launch of the return rocket. And we had joked when we were writing the proposal that based on how things have gone over the last 20 plus years at that point, eventually there's going to be like a SpaceX astronaut pushing the button on the plunger, to launch the rocket, like an Estes rocket from the surface of Mars. So we joked that it might happen like that. I hope that they don't make a deal with the Chinese and have the Chinese bring back the samples. It's hard to tell what's going to happen. But it's been a program near and dear to my heart because I worked on it We won it 5 or 6 different times
Mhm.
over my career. It was interesting. Great team. They're now all starting to work on other things as the program got shut down here recently. Wanted to bring in hypersonics. We do the boosters for a couple of different systems. On the left is the Arrow, and don't ask me what Arrow stands for, but it's a Lockheed Martin system, air-to-ground missile, launched off the B-52. One on the right is, what is it now, Sherry? Is it HACM? HACM is called for the Air Force. We make the booster and we make the scramjet engine for the air breather on the front end. Assembly of the scramjet will be done at our facility in Elkton. The design teams are primarily in Florida and New York on that for the air breather, but the solid booster stuff is all done.
Quick definition of hypersonics meaning anything.
Greater than Mach 5.
Yeah.
Greater than Mach 5. So reach out and touch somebody pretty fast. So the current Tomahawk cruise missile is basically high subsonic. So less than Mach 1. So get there 5 times faster. So really, from very humble beginnings, we grew at one point to about 900 people, and then shrunk back down to in the 80s, or no, early 90s, right before Sherry got here at Elkton, to about 280 people. We were one step away from being closed, and then we won the SM3 third stage rocket motor and the DAX for that. And a lot of these firsts and several of the other programs, I'm in the process of getting organized to write a book about it. I've got to get all kinds of permissions from the company to get copyright on a lot of the materials, including all the papers that I wrote. Got to get them reapproved in the new Northrop system for that, even though we were publicly released. All the stuff you saw tonight was publicly released by former companies, ATK, Thiokol, Orbital ATK, et cetera. So one of the ones I didn't talk about, GPS. All the flights of GPS that went off the Delta II launch vehicle, we had 2 motors on each mission, one on the spacecraft and one as the third stage of the Delta rocket. It's a huge program. There's several others that are equally important that we were part of. We didn't make the fancy part, the spacecraft part, but we got the spacecraft to where it was supposed to get. And it was always fun. We have a great bunch of folks that work there. I miss a lot of the people. I don't miss all the meetings I used to have to sit on. But if you're willing, I could take some questions now, or we can show the videos and then take questions. Or
Let's see if there's any questions. Yeah.
Yeah, I got a question.
Yep.
How long before at what point did you ditch the phenolic and go to the carbon fiber?
Well, we went to the carbon fiber for a lot shorter time than you would think. The West Star and Palapa failures that I mentioned, those happened in the 84 timeframe. So we flew several motors of the 37-inch diameter and 30-inch diameter that had carbon nozzles, continue to fly those. 48s were grounded until we re-qualified with carbon phenolic nozzles, mainly for insurance purposes. We were in lawsuits from 84 up until about 95, 6, 7 timeframe when the last lawsuit got settled. We figured out eventually what caused the issue is it was a chemical wash at the rayon white goods stage before it was even carbonized. That was the issue, and basically weakened the ability for the layers to stick together. You want them to kind of stick together like Velcro, and they didn't. So you have a question?
Yeah, you mentioned, I think you used the word controllable motor. Does that mean throttleable?
Yes, fully
How does
throttleable.
that work on a solid propeller?
So we currently, most motors throttle by design. So we can make the thrust go up, we can make the thrust go down or stay flat just by the design of the propellant charge. by doing it by mechanisms like the ACM, basically we have a fully proportional valve that can fully open and fully close. We got to keep enough area open to control the pressure, but we can modulate the pressure by the amount of area we have open. If we want to, in vacuum, it'd be easier in vacuum than it is at sea level. We could open up enough area that we could shut it off. To turn it back on, we would need another igniter. But we've done all those things on test articles. The fully controllable solid is what is being used on the interceptor systems. We've been in development of those since probably around 1990, early 90s, late 90s timeframe, so over 25 years.
So this is controllable by the design.
Well, design of the charge
timing of the
and then
changes
the
are
mechanism.
fixed at the beginning, or is that adjustable by?
So most motors are fixed at the beginning. For these with the mechanisms, the hot gas valves on them, we can change it at any time. So on command, as part of a control system to do an intercept, we can modulate how much acceleration we need at the time of the mission. So yeah, it's the books say that you can't do that, but that technology has been around for over 25 years now.
It's a basic question. How do you ignite these motors exactly?
Well, you can ignite them with a lot of different things depending on the conditions at the time. So sea level, it's a lot easier to light it than it is at vacuum because I need a certain amount of pressure just to get the combustion going. The bigger motors, we use a small rocket motor to ignite the bigger rocket motor. So we call those pyrogen igniters. Pyrotechnic igniters are basically baskets of pyrotechnic material, including black powder, boron, potassium nitrate, and several other compounds that can be used. But basically, we have an electric squib that lights that then blasts all of that material onto the surface and also generate enough pressure to sustain the combustion. So it's a timing thing and it's an energy thing. How much energy do you need over what amount of time at what pressure, ambient pressure condition? Yes, sir.
With so many companies working on these projects together, I'm curious, like how integration kind of works. I mean, do you, when the project is starting, would you get very specific orders, or was there a lot of work?
So most of the programs, we get a set of specifications in describing what they want. Frequently, they want 10 pounds of performance in a 5-pound bag. And then we have to negotiate, okay, you can only get 5 pounds of performance unless we do this. And you might need to pay an extra amount of money to do those things. So where is the pain point between their desired performance and the ability to get the performance? The ACM, they looked at an alternate liquid system for that as well. And it wouldn't package in the same volume that we have, right? So that each valve, there was 8 of them on the ACM, being about a foot long, had the same maximum thrust capability as the OMS engine on either side of the shuttle tail, right? Those 2 small nozzles either side of the tail up top. Those engines are a little over 6 feet tall, weigh about 500 pounds. Our valve weighed 25 pounds, including the cable and the actuator. So think of, there's no way you could put 8 of those OMS engines in a 32-inch diameter. Just no way you could do it. Ready to see some videos, or are there any more questions online?
We can grab, questions online. We can certainly grab questions after the videos,
Okay.
but I know tests are always the highlight of my workday, so.
All right, so presentation. So this is the leaf hover test for the Hughes front end. at the hover test facility at Edwards Air Force Base.
3, 2, there's 1.
So the propulsion system's about 5 inches in diameter and about 13 inches long. 10 nozzles. Proportionally controlled by pulse width modulation. So these were fluidic valves at 200 hertz frequency, command frequency. So that's an amazing thing. That turned into the SM3 system at a bigger scale. FMs or flight missions. This is a video from probably close to 15 years ago. What was different about this interceptor than the GMD program was that the entire time Navy crew were operating the system, not contractors.
The Missile Defense Agency and U.S. Navy achieved the first simultaneous engagement of 2 ballistic missile targets from the sea.
So in all the engagements around Israel, quite a few of these missiles have been fired and all worked rather well.
Are actually smaller than typical ballistic missiles used by our adversaries, and therefore represent a very stressing target to acquire, track, and intercept. The USS Lake Erie was positioned over 250 nautical miles away from the launch point off the coast.
So those are the Aegis ships.
The ship's crew was not informed of the exact target launch location, time, or trajectory. The ship's commanding officer is provided with an operational scenario and intelligence typical of a real-world scenario. The ship's crew programmed the Spy-1 radar to perform a search designed for achieving BMD mission objectives. As the targets rose above the horizon, the Spy-1 radar acquired each target and placed them in track. The weapon system automatically developed a unique fire control solution for each target. Due to the very short timeline for this threat, the weapon system was operating in auto-engage mode. Several minutes after target launch, the ship's crew fired the first SM-3 Block 1A. Seconds later, the second SM-3 was launched. Each missile flew towards a predicted intercept point based on in-flight target updates from the ship. Roughly 30 seconds prior to intercept, the first kinetic warhead was ejected from the third stage. AW acquired the target, performed aim point selection, and maneuvered.
So basically, it only sees about a pixel, so that's why they move it around to make sure the pixel isn't burned out.
Its target. Mark India. Another direct hit. The kinetic energy for the impact is calculated to be in excess of 125 megajoules, the equivalent of a 10-ton truck traveling over 600 miles per hour. Numerous ground, sea, and air-based sensors observed both intercepts. With the successful completion of FTM-13, Aegis BMD and SM-3 have successfully intercepted 11 ballistic missile targets, and for the first time engaged 2 ballistic missiles simultaneously. The engagement was performed under strict operational testing conditions. In addition to USS Lake Erie, several other ships, aircraft, and ground-based assets participated in the event and tracked the target. Japanese destroyer JS Kano participated and successfully tracked both targets. The Missile Defense Agency and the U.S. Navy teamed with their industrial partners, Steve Martin in Morristown, New Jersey, and Raytheon in Tucson, Arizona, are continuing to improve and deploy this Aegis BMD capability with the delivery of additional Aegis BMD ships and SM-3 Block 1A missiles. Aegis Ballistic Missile Defense.
And you can find a bunch more of these type videos online for SM-3. So this is an ACM test, development motor 2, fired on St. Paddy's Day in 2010. And the top view is really interesting. You'll see all 8 nozzles being actuated from fully closed to fully opened. And the duty cycle we had was really verifying requirements for all kinds of different command scenarios. So again, this was done at the time we were ATK. So about 28 seconds of total burn time. And that's a solid rocket motor doing that. That's my favorite part.
NASA chief engineer was sitting in front of me and she said, now you're just showing up.
Yeah. The first test we did in December of 2009. And I was up against the wall in the conference room. And I was pretty confident that things were going to go right, but you never know, right? All the testing showed everything was connected right, everything was going to work right. We ran through the duty cycles and all that. Everything worked. But you just don't know till the hot gas goes through it that everything's going to be fine. And NASA people everywhere, Sherry was in the room too. The two NASA principals, one I went to grad school with at Purdue, the other one I went to high school with. So it was pretty cool that got to work with people I knew pretty well on that program. Now this one, hot gas high thrust test number 11. This was the first test of the new drain design and new valve design for the fully compliant NASA requirements. And it was one of the first tests we ever used a drone to watch. 5, 4, 3. We only had 3 valves, so we could get really good data in the different directions. And we were over ATK at the time.
Elton?
In Elton. Yes.
Yes, that's some of those earlier test videos were not from our facility, but I mean, can you talk about where this has?
Yeah, this test was at Elton.
Yeah.
The pad out there is by the Little Oak Creek. It had our altitude facility, which has since been moved over, and a new altitude chamber was put on it about 15 years ago or so. But the original site was here, where they did the altitude testing of the surveyor motor back in the early 60s. So this was a shot at Elton. This is one of the qual motors for the human spaceflight version. It has a similar duty cycle to the other one, but as you can see, from the side, you're not going to see nearly as much.
6, 5, 4, 3, 2, 1.
And they actually had a good day for that one. The first 2 tests, we had the creek nearly flood, and we were on night watch to make sure that if it was rising too high, that we would take the motor out of the stand. Then this is the altitude abort. This one was called.
That is not our facility.
No, this was down at the Cape, I believe. So they were trying to mimic the flight trajectory of the SLS. That little bit of smoke that you saw on the side of the plume was from our gas generator for the Peacekeeper first stage motor that was used here. Surplus motor after Peacekeeper got retired. So this one was really to do an abort at basically max Q, one of the hardest places in the trajectory, highest dynamic pressure. So they get up to about 45,000 feet, right around the transition to supersonic in the SLS. The abort motor fires and the ACM fires at basically the same time. We control pitch and yaw of the separated stack with the capsule. They come off at about 12 to 14 Gs. You can see our little plumes up at the top. And this maneuver you're going to see here shortly is done to make sure that the heat shield is in the right direction for the parachutes to come out and to re-enter if they're at a high enough altitude. And then the jettison motor fires. to get rid of the whole stack above the capsule so the parachutes can come out. Hopefully, we'll never have to use that.
And I say, hopefully it'll never happen again.
But that'll occur. Flight of Artemis 2 is going to happen here in the spring of 26, somewhere between April or February and May, I guess, is the time frame. 10-day mission out to around the moon and back.
Is that still on track?
Yeah.
Oh, okay.
Yeah. They're hoping for the early part of that total time frame.
Okay.
If they wait too long on the pad, we have capability to recharge the battery for the ACM on the pad, but they don't really want to do that.
Mm.
So it depends how often the NASA folks want to do duty cycles, because they could burn down our power in the battery enough where they have to do a recharge too. But then, since it's at the top of the stack, it's hard to get to. So they really don't want to mess with that. But that was one of the things in our requirement space that we had to make an allowance for ground recharge. So those are all the videos I had. Any more questions?
Did you ever get to go down and see shuttle launch?
I did see a couple shuttle launches.
Okay.
One while I was in grad school from the Causeway.
Okay.
And one from near the VAB.
Okay.
When I was in at work.
But not in official capacity, right?
No, just as a guest of
yeah.
So Utah would usually send a couple busloads of folks, equivalent, send them down there and let them watch as part of the outreach program for the space flight.
Mm-hmm.
And got to go as part of the Elkton group. Also saw the aborted attempt to fly the Orion capsule on the Delta IV.
Okay.
When they did that test flight. I didn't wait around for the next day to actually see it launch. They had some issue that they couldn't launch. I did watch the Ares 1X. I had been the chief engineer for the first stage for that as a test flight for the Ares 1 vehicle. So that would have been an SLS booster effectively with a liquid upper stage and then the capsule. So they were going to launch the capsule separately on a smaller launch vehicle. And as the SLS big booster was intended initially as only cargo. But it didn't turn out that way based on how the funding went over the years. But that was the original intent. The big SLS booster was going to be called Ares 5, and the human launcher was Ares 1.
I'm curious what your perspective is on SpaceX taking over from NASA, or taking over, basically replacing NASA. Do you think that's happening, or is it? Or would you say they're just another participant, another subcontractor in the scheme of things?
They act like they're going to take over. NASA doesn't like that position, obviously. I think there's going to be a place for NASA to continue to direct missions, but the more folks like SpaceX are involved, the more it'll be a contract thing where fly me to this orbit and whatnot. The days where NASA controls everything and, they're basically half the cost of SLS and Orion, and it's in an oversight role. So it's out of whack with the hardware value that they add. So the cost of those programs are probably inflated a lot by the staffing that they have on it. And they tend to not get rid of the oversight staff once a vehicle becomes operational. Shuttle was a big example of that. Sherry could talk for hours on the amount of NASA insight and oversight that was on shuttle when she was out there in Utah. So I saw a little bit of it from the work I did when I was out there for a couple of years. But Not like Sherry saw it. She was on the shuttle program and saw it directly. NASA's in kind of a tricky spot. Are they a technology developer, or are they a prime on these missions? They tend to want to be a prime, but they don't do the prime work. They tend to verify or validate everybody else's work. So it's really double the amount of work. And eventually you got to say what value you're adding by doing that oversight. So what percentage of the program should that be? And then if they want to continue to fund technology development, they could accelerate some of that stuff that's too risky for us to do as contractors. They should be the ones doing it. So I think there is a role there, but it's going to evolve, and I think we'll see that over the next 4 or 5 years. Good question. It's a hard one to answer because it's hard to tell which way the winds are going to blow on how that's going to happen. I've told Sherry and other folks, I thought for a long time that NASA, like the military, should have a BRAC. There's too many centers doing too many, niche specialized things that they don't necessarily need all those centers. I know why they have them in the various states is for votes, right? That's not lost on me because you need the political support to have it. But the bottom line is I don't think they needed all the staff that they had. So it depends on your viewpoint as to how much value they really have. It hurts me that the science part of NASA is getting hurt pretty bad. It really does. Any other questions?
And anybody online, just want to make sure if we're having any technical challenges getting questions in. Yeah. Last chance.
Did I bore you to death?
Otherwise, let's give another great thank you for Dave. Have refreshments, so please join us and hang out and have some other conversations or further questions. As always, keep an eye on the groups.io. Participate in an outreach event, AP-SIG, book club meeting, or if nothing else, come back in a month and we'll hear Sherry's perspective, the inside view of the Challenger disaster. So thanks for coming. We'll see you guys around.
Okay.
Thanks.
Thanks again.
Night, everyone.
Good night.
Night. Night all.